Well, welcome to Calculus. This is Chapter 1, Section 1 homework. And I have two homework assignments. I have problem number 8 and problem number 9. So we're going to do number 8 first. So part of the idea of calculus, there's two parts of calculus. There's differentiation and there's integration. Both of those are dependent upon the concept of limits. But the idea is that from a derivative standpoint, which is problem number 8, is that if you looked at the slope of a line, if you wanted to know the slope of a line at a particular point here, that if you take that point of interest and a point that's some distance away, some finite distance away, and you know those 2 points, then you can draw a straight line between those two, and you can find the slope of that line just from things that we learned in algebra many, many years ago. And as you move this blue point closer and closer to the black point, the slope, which is going to continue to have a finite value, is going to get closer and closer to the actual value of the slope at that point. And the slope of that line at that point is going to be tangent to the line, and there's only going to be one point that defines it. But as you take the limit, as this distance from the blue to the black dot gets smaller and smaller, the approximation approaches the actual value. So what we do in this particular case is we're just going to do some approximations of the slope. And what they say is consider the function f of x equals the square root of x. So that's the function, if you remember back from pre-calculus, the square root function looks something like that. And we're looking for, at the particular point, 4, 2. That means at x equals 4 and y equals 2, and that would be this point right there. So what we're doing is we want to approximate that, the slope of this line at that particular point. And what you can do is you can take various values of x, specifically x equals 1, x equals 3, and x equals 5. And each one of those, using this as one point, and the point 4, 2 as one point on the line, and then using these 3 as the other point, you can find out the slope just by using the definition of the slope. And those are going to approximate the actual tangent line, which is going to have a slope of something like this, where it only intersects or touches the curve at one point. So part A says graph f, which is what I did, and the secant lines passing through the point. Okay, so the 3 lines are going to be, here's one point, there's the other point. So that's the secant line at using point 4, 2 and 1, 1. And then we have the next line, which is going to again go through point 4, 2, but in this case, let's see, we use a different color, blue. So we start at 4, 2, and we go through 3, the square root of 3. So then it would look something like that. And the final one, I'll just use black, would be between point 4, 2 and 5, the square root of 5. So those are the 3 points, and you can see as x gets larger, the slope of the line gets lower. It's not as steep. So that's the graph. Find the slope of each secant line. So this is part B. The slope, of course, of a line is going to be equal to y2 minus y1 divided by x2 minus x1, which is the rise. This is the rise divided by the run. Now, in this case, I'm going to let y2, x2, y2 be the point 4, 2. And then we're going to let x1, y1 be, take 3 values. So x1, y1 for the first case is going to be 1, 1, x is equal to 1, the square root of 1 is 1. The second point, the second case is x1, y1 is equal to 3, comma, the square root of 3. And the third case is x1, y1 is equal to 5, comma, the square root of 5. So to find the slope, let's call this x, y, and z. Well, it's not good because we're already using x and y. So I'm just trying to m in. Let's say this is case m, this is case n, this is case o. So for case m, the slope of the line y2 is 2, and y1 is 1, x2 is 4, x1 is 1, so we'll get 1/3. So that's the slope, the red slope of the red line. Okay, then we go to n. That's the blue line. And so we have 3 minus 1. That's incorrect. It's equal to the square root of 3 minus, sorry, let's try this again. 2 minus the square root of 3. So that's y2 minus y1 divided by x2, which is 4, minus x1, which is 3. And I'm just going to plug it into my calculator, which I've got to find. I haven't used it for a couple months here. So just hold on. Still have batteries in it. It's still working. I know it's got batteries. Hopefully, let me just make sure I'm still recording here. Okay. No, still working. Okay, so you take 2 minus the square root of 3 divided by 1, and you get 0.268. And of course, this one is 0.333. And O is a slope of, in this case, okay, so we have y2, 2 minus square root of 5, which is y1, x2, which is 4, minus x1, which is 5. So these both are going to be negative. So we get 2 minus square root of 5 is negative 0.236 divided by negative 1, which of course the negatives cancel out, and you get 0.236. So you can see the slope is getting lower, as I said it would be. Now, the actual slope at this point is really going to be probably an average of these two, because as you go through here, you have this point here and that point there. You go from the blue curve to the black curve, so the black curve is using points after the point in question, and so it's going to be some average of those two. So use the results from part B to estimate the slope of the tangent line at 4, 2. So part C, we would just say the slope at 4, 2 is approximately equal to 0.268 plus 0.236 divided by 2. 0.268 plus 0.236 divided by 2, and you get 0.252. So that's the answer. Now it says, describe how to improve your approximation. Well, what you would do is you would choose points, x values, closer to 4 than 3 and 5. So you might try 3.5 and 4.5, or you might try 3.9 and 4.1. And with each one of those x values, you can calculate a y value. These slopes are going to get closer and closer to the actual slope at that point. And if you take the average, then you can get a better number. So you might think the exact value is probably around 0.25, and it turns out it is exactly 0.25, which we'll learn in a couple of chapters. But for right now, this is a pretty good approximation. Okay, this is our second problem. And the first problem was problem number 8, which showed a way of approximating the slope of the curve at a particular value of x and y. In this case, what we're looking at is we want to find the area underneath the curve. If you look at problem number 9, you'll see that we have a curve which looks like kind of 1 over x, which is actually 5 over x. So it's a reciprocal type relationship. And it says find the approximate the area bound by the region y equals 5 over x, which is the black curve, y equals 0, which is the x-axis, and then x equals 1 and x equals 5. And basically what the two cases are where you're looking at a different size rectangle. So it's the same curve, but you're, first case, using 4 rectangles to approximate the area, and in the second case you're using 8 rectangles. So all we have to do is find the area of the individual rectangles. And if you look at them, look in the book, you see the first rectangle left has a height of 5 and a width of 1, and then the second rectangle has a height of I guess it would be 5 halves and a width of 1. And so all you have to do is add those areas up. So we basically have the total area, which is what we're looking for, is just the summation of the 4 individual areas that we have, shown by the 4 rectangles. And the area of a rectangle is just the height times width. So in this case, the first rectangle has a height of 5 and a width of 1. They all have a width of 1. The second rectangle has a height of 5 halves, because x is, in this case, it was 5 over 1. Here it's 5 over 2 times 1. The third rectangle has a height of 5 thirds times the width, which is 1. And the fourth one has a height of 5 fourths times 1. So let's just do this as a fraction, just for a little exercise. So if you look at it, we've got halves, thirds, and fourths. So the common denominator would be 12, the least common denominator. So let's just multiply it out first. Well, it's 5 plus 5 halves plus 5 thirds plus 5 fourths. Okay, so to get it into twelfths, we're going to multiply this by 12. So we'll get 60 twelfths. This one, to get 12 in the denominator, we need to multiply by 6. So we'll take 6 divided by 6 times 5 halves, which will give us 30 twelfths. We need to multiply this by 4. 3 times 4 is 12. So 5 times 4 is 20. So that's 20 twelfths. And then to get 12, 4 times 3 is 12. So we're going to multiply 5 times 3, which is 15. So we get that. And then you add all those little fractions up. Or you add them, let's add the numerators because we have the common denominator. 60 plus 30 plus 20 plus 15. And we end up with 125 twelfths. And can we divide that? Can we simplify that? Again, this is some review here. So we can't divide by 2. So we can't divide each by 2. So that's not going to be a common factor. 3, can't divide that by 3. How do you know? Because if you add the numbers 1, 2, and 5, which is 8, you can't divide 8 by 3. Therefore, you can't divide 125 by 3. You can't divide 12 by 3. Okay, so that's 3. That's not going to work. And if 2 didn't work, 4 doesn't work. 5, you can divide this by 5, but not that by 5. So, so we pretty much run out of options here as far as simplifying. Now, what happens in the second case? probably the best thing to do is to make a table. So I'm going to make a table 8 by 3. We're just going to fill this out. So what I'm going to have is I'm going to have x, which is the x coordinate of the left-hand corner of the rectangles. And then I'm going to have the y value, which will be the height of the rectangle. And then I'll multiply them together to get the area. And then I'll just add them all up to get the total area. So you can see we start at 1. We go to 1.5 is the next one. 2, 2.5, 3, 3.5, 4. Oh, actually I had an extra. Okay, so we're going to have 1, 2, 3, 4, 5, 6. Something I missed something up here. What did I do? 1, 2, 3, 4, 5, 6, 7, 8. Oh, 4.5. Because we go and then 5, but we don't do 5 because we're just looking at the left-hand upper corner. So then you do y. So you're going to take 5 divided by 1, which is 5. Then we take 5 divided by 1.5. I'm using the calculator now, so it's 3.33. And then we have 2 divided by 5, pardon me, 5 divided by 2, which is 2.5. 5 divided by 2.5 is 2. 5 divided by 3 is 1.66. 5 divided by 3.5 is 1.43. 5 divided by 4 is 1.25. And 5 divided by 4.5 is 1.11. Okay, so those are the heights of the rectangles. The width of the rectangles is 0.5. So what we're going to do is we're going to take this number, the height, times 0.5. Here we took the height times 1 because the rectangles are twice as much. So if we multiply all these by 0.5, so 5 times 0.5 is 2.5. 3.33 times is 1.66. 2.5 times a half is 1.25. Half of 2 is 1. Half of that, 1.66 divided by 2 is 1.66 divided by 2 is 0.83. Just going to carry out to 2 decimal points. 1.43 divided by 2 is 0.72. 1.25 divided by 2 is 0.63, and 1.11 divided by 2 is 0.56. So those are the areas of those 8 rectangles, and then we just add all those things up, and we should come out to about the same answer as we got over here. So let's go ahead and put that in decimals. 125 divided by 12. And you get 10.4. Okay, so that's it. These 2.5 plus 1.66, actually 1.67, that's rounding up, plus 1.25 plus 1 plus 0.83 plus 0.72 plus 0.63 plus 0.56, and I get 9.16. So that's the area approximation there. This is the area approximation there. And the actual answer, I'm going to do this over here so you don't see it because this is something we've done for quite a while, but is going to be equal to, and it turns out that the answer, the exact answer is going to the total area. The exact answer is 5 times the natural log of, no, actually it's the natural log, hold on a second. it's, 5 times the natural log of 5. So hopefully remember natural logs of 5 times the natural log of 5 is 8.05. So that's the exact answer. And you can see the first answer, which used 4 rectangles, had 10.4. As you went to the smaller rectangle, it went to 9.16. And if you kept adding rectangles, making the rectangles thinner and thinner, then the answer is going to approach 8.05. And the exact answer is 8.05. And the process of approaching something is what we call limits. It says, part B says, describe how you could continue this process to obtain a more accurate approximation to the area. And the way it is just to make the increments get smaller and smaller in the x direction. So instead of having a delta x of 1, you'd have delta x of 0.5, which is the first step. Then you get a 0.25 and 0.1, and just make it smaller, smaller, smaller. You would have more and more rectangles, and the calculation would become more and more, well, not more difficult, just longer. But what we're able to do using calculus is we can come up with an exact answer analytically and get the exact answer.